Welcome back, everybody. Today, as we mailed to all of you, we do not have access to our regular lecture hall, and that's mainly due to the what's normally called the high school post-education day, or faglig pedagogisk dag in Norwegian. However, tomorrow we will be back to our regular classroom. So it's only this day which is an exception, where we don't have access to our regular classroom. So as you can see from the Jupyter notebook here, we are going to enter a new topic now, and this is a topic of decision trees and ensemble methods, random forests, etc., etc. And these are widely used methods in both classification and regression. And this is the third last topic this semester. After decision trees, ensemble methods, and random forests and more, we are going to look at another machine learning method, which is also widely popular, which is called support vector machines, again, both for classification and regression. And if we get time to it, towards the end of the semester, we're going to look at some of the unsupervised learning methods like clustering and even principal component analysis. Now, what I wanted to give you today is first the overview of what these decision trees are and why they are so popular. They're actually used to make ensembles of trees, and these ensembles of trees, they clearly become woods or forests. But then they can also be used, since they're very easy to train, they can then be used as an input to methods like boosting methods, where you actually use a decision tree as a weak learner and you improve upon it. Because the decision trees, being that easy to train and run, they can provide a starting point for the description of a given data set. And they're widely popular and they're very intuitive. And it's easy to interpret the results when you have performed a calculation with a decision tree. And we are going today to look at the basics. We are going to look at how we can write a code for decision trees. We're going to look at classification and regression algorithms and how we can visualize the results in terms of a tree. So the decision tree reminds us very much of the kind of game many of us played with when we were kids. We were sitting in the car on a long ride with our parents, and then you had this 20-question kind of game where somebody would think of something, and then the other ones got 20 questions, and they were then going to nail down what that person had been thinking of. And you had typically yes/no answers every time you made a question. So decision trees can be made like that in a very easy way. So let's try to dive into the decision trees first. So there's a small digression which I wanted to mention to you as well. If you're interested in one specific and very fast-growing area of applications of machine learning, which is about applications and techniques for fast machine learning in science, where you look at both hardware and software development for efficient implementations of machine learning methods for scientific discoveries. So if you have time, take a look at this article here. You might find it very interesting. So decision trees, the overarching aims, we are going to start with the most basic algorithm. This is actually called the classification and regression tree algorithm, or just the CART algorithm. So we are going to go through that today. And this basic algorithm can then in turn be used to build more complex networks or ensembles of trees in our case. And that can span from lookalike trees, homogeneous ones, or you can make them more heterogeneous. There we have things like random forests. If you're looking at more homogeneous trees or forests of homogeneous trees, the same type of trees, we end up with a method which is called bagging. And we are coming back to that one, what is meant with bagging. It's actually based on a bootstrap, where every bootstrap ensemble represents a new tree. And then we have an extremely popular algorithm, which is called gradient boosting, or just extreme gradient boosting, which is not an algorithm itself. It's actually a highly efficient and highly parallelized library, which is just called XGBoost. And this is a method which has actually won many competitions in both classification and regression analysis of data sets. So decision trees are supervised learning methods used for both classification and regression tasks. And the main idea of a tree is to find those descriptive features which contain the most information regarding the target feature. And then you would split the data set along the values of these features such that the target feature values for the resulting underlying data sets are as pure as possible. So we are going to define today what we mean by something which is as pure as possible. And the way we build this up from top down is to start with a root node. That's the main node or the main feature of the system. And then we are going to look at interior nodes and the final leaves or the final nodes, which are just called leaves then. And then in between these different entities, they will be connected by branches. So everything linked up with the trees here is something which is going to be used again and again in the description of the quantities which we are going to look at. So before I just show you an example of a typical regression problem and a classification problem, I just wanted to show you this image which you see here, and hopefully you can see it. Let's see if we can increase a little bit. But this is an example of a classification problem based on the cancer data. And in this specific case, we have the worst perimeter, which has something which is called a Gini factor, which we're going to define today. And you can also see the amount of quantities here, which are classified as benign tumors and malignant tumors. And then it splits everything in a binary way. So we have this true and false continuously. And this tree was actually produced using scikit-learn and the Wisconsin cancer data, which we have been mentioning many, many times. So the general features of a tree is the typically from a top-down approach. You would have a leaf which provides the classification of a given instance. A node specifies a test of some feature of the instance. A branch corresponds to possible values of one of these attributes or features. And an instance is classified by starting at the root node of the tree and then testing the attributes specified by these nodes. So let's take a quick look at the way we could think of a classification tree. So let's take a quick look here at the whiteboard. So a typical classification problem with a decision tree could look like this. Tree classification problem. And what we are going to do now is to look at a specific data set, which we are coming back to later, in order to actually set up the final problem. So what we could have now could be data sets on grades, which we get for a given course. And we could now have attributes for the final grade. So the final grade is the output. And the attributes or features, they could be the grade trend which we have. So we could be on the rise, or we could be below an average grade of a given cohort of students. We could have the number of hours we've been studying for a specific topic. So let's call this the number of hours studied. Because of hours, the number of hours we have studied. And then we could look at another parameter which could influence the final grade in a specific course. So that could be the number of hours we have been sleeping. And you know, having a good amount of sleep is actually very important. Actually, the deep sleep is perhaps one of the most important ones, the deep sleep and the core sleep. And then the output, so these are the attributes which we have. As we have been discussing before, the features or the properties of a given system. If we are looking at this cancer data, I mean, the attributes or the features could be the perimeter of the tumor, it could be the radius, it could be the thickness, and these properties which we have mentioned several times. And then finally, we would have the output here. And then from the output, we would then look at the grade of for a specific course and whether this grade is above or below the average. Above or below the average grade. And suppose we have collected data like this. So we have followed a group of, let's say, 30 students following a given course, and we looked at their grade trend, and this grade trend could be above or below the average of these 30 students, above or below the average grade. And similarly, we could look now at how this influences the final grade for a specific course, and how this can be also correlated or possibly correlated with the number of hours we have studied and the number of hours we have slept and relaxed. So this could be just an example of a data case, and we're going to bring this up again a little bit later when we are going to detail how we can write an algorithm for decision tree. So the way this could look like now could be something like this. We would find a root node, and in order to anticipate what you're going to see when we do the actual calculations, this is going to correspond to one of the features. So this will be determined by the grade trend. So that's going to be the most important feature, which determines with a given likelihood the final grade for a specific course. And then this splits into branches. So we normally call these for branches. And we would have false and true. Or yes or no, 0, 1, or whatever. And normally, from a computational point of view, what is normally done is to use a binary splitting. You can actually have more than a binary splitting, but then the computations take a little bit more time. So the standard is actually to use a binary split. So this would be something which really mimics this kind of 20 question games, yes, no, false, true, etc. And then we would continue like this. So if this is the grade trend is the one which has the biggest impact on whether you get a specific grade in that course which is below or above the average, this would probably, and you might expect that is most likely correlated with the hours studied. So not all the times will you get a clear correspondence between the number of hours you've studied and the final grade, whether that's above or below the average. So this could now lead to, again, a kind of false and true case. Sometimes there are no more cases when you do false here. That means that you could end up in a situation where all the grades are below average. So that means that this would stop here. And this would just be called the final nodes or just the leaves or the leaf nodes. So this would now be just called for the leaf node, or just simply leaves. And that's where it terminates. And that means that inside this slot, which you see here, you have a pure set of outputs, which means that it's the same as you have just one type of final results. So that means, in this specific case, it means that you will have grades which are just below average. And when you then go back here to the hours studied, maybe this terminates here and this terminates here. This node here would be called an intermediate node. And finally, we have the leaf nodes here. Or they're simply just called leaves. So you see this is a kind of upside down tree. So you start with a root node, so you take a top down approach. You try to find the most important property. And the thing which is nice with a decision tree is that you can actually provide something like this to your friends and tell them that this is the way we are going to interpret the data. It's pretty clear, it gives a clear message, and you can split it up in this kind of false and true, and then indicate those properties which are the most important ones. So as we will see from the data set which we are going to set up in order to run a calculation of this decision tree, we will find that the grade trend or your average grades is what is most important when it comes to the final grade, whether you get a grade which is above or below the average in a specific course, which is not unexpected. And the hours studies is also something which is going to play an important role, whereas the hours slept has often less influence on one specific course. Clearly, it has influence on our general physical, situation. Okay, so I'm going to jump a little bit back and forth between the whiteboard and the Jupyter notebook, but this was more meant for us to set up a typical classification problem. When we now go to a regression problem, the way we actually deal with regression problems is that we divide the domain of outputs and inputs in terms of geometrically equal areas in forms of squares. So let's look at the regression case. So in the regression case, what we end up doing, suppose now we have a set of variables, x1 and x2 here. Then suppose we have some observations like this. So I have some circles, I have some crosses, and I have some further crosses here, and I have some pluses. So what we could do now is to define some specific areas, and we could now say that, okay, we have this specific area here, which is split like this. So we have a variable which we simply call v here. And then we have another demarcation line here, which we can call for w, like this. And then we can start splitting it up again in smaller areas. But let's just split it like this first. Now, what we could do then is the following. We could have a test now if x1 is less than v. So we can call this different regions. So we have an R1, we have an R2, we have a region R3, and we have a region R4 here. So if x1 is less than v, then what we would have is that we would have regions R1 or R2 here. So that leads now to two regions. So we have R1 and R2, and we can now have a new test here. So if x2 is less than w, then the final output is just an x here. On the other hand, if we go to R2, then we can have an if test here. So this is the final if. That's the only possibility which we have. If we have the R2, which means that if x2 is less than w2 here, no, sorry, if x is larger, x1 is larger than, let me just cancel that one. So if x1 is larger than v, larger equal, then what we can do then is that we can go into this, if that is true, then we have to test. So this will be the true case. And if it's false, we already tested that one. But if we have true here, then we have to check if x2 is less than w, which is the other boundary here. Then if that is the case, then we would be in the region which we have called for R2. If not, we have then to look at either region R3 or the region R4. And this will just continue all the way down here till we have nailed down the final values depending on X1 and X2. So what we are doing then when we deal with a regression problem is that we subdivide our domain into different regions, and then we have all these if tests. If X1 is less than V, then we can go either to R1, or if it's false, we go to R2, etc., etc. Now, the thing now is that when we do a regression, what we are going to have as an algorithm is that the prediction we end up with is that we predict the mean value for these different observations we have in the domain R1 or which we have in the domain R3 or R2 and R4. We can then, if you now think a little bit more ahead, you'll see quickly that if we now can subdivide these areas in small and smaller areas, so we could now think of making smaller areas. So we could think of actually making areas like this. So a further subdivision, which means that if we now are in this specific region, our prediction is the mean value of the observation in this region here. And in this case, there is only one variable. And that means that the prediction we are going to make is exactly this value here. Now, you see easily that this is something which most likely can lead to overfitting, because we can actually predict precisely every single output which we have here. Yeah, right. So I think I wrote R3, no, R2, but it should actually be R3. That's correct. I see that. Sorry for that. So this should be R3 here. Thanks. I was a little bit, I actually confused myself here. Thanks. And I just invite you to actually fill in the rest of the form here. But you can subdivide these regions to regions containing less and less data points. And then you can nail down precisely the expectation value or the prediction which you're going to make to be exactly that given number. Now let's go back to the Jupyter Notebook and actually look at an example where we now can make this tree deeper and deeper. So if you look at the model which we have here, if I'm now making smaller and smaller regions and narrowing down the number of data points which I have in a given region, like this one, that means that I'm going to make my tree deeper and deeper. Or you could think of that higher and higher if you turn the tree upside down. So that means that we can then define a variable which is called the depth of the tree, and we will see that quickly. So if we make the tree deeper and deeper or higher and higher, that means that we can then limit the number of observables which we have in a small box here. And the prediction is the mean value of the observations we have in a small region. So let's take a look at how we could run this using scikit-learn. So let's take a quick look at the Jupyter Notebook. And in the case here, we have a simple program where we are setting up a random walk in one dimension. So we can just jump back and forth here, and we do this at 250 steps. And by running that one, what we want to do now is to, after we produce the data, the random walk data, where we just go up and down, what we want to do then is simply to perform a linear regression, a polynomial fit. So we're going to try to fit the data with a polynomial of degree 2. And then we are going to get a little bit more ambitious, and we're going to fit a polynomial of degree 10. So if we take a look at that, what we are going to get is something like this. So this is our polynomial fit. And the green lines These are just our random walkers in one dimension. And you can see the distance you have traveled as a function of a given number of steps. Now, if I try to fit this with a second order polynomial, you see that the result here is actually not very impressive, as expected, because the data sets are actually pretty, how to say, pretty random, jumping up and down here. And if I try to fit a 10th degree polynomial, I'm getting closer to the trend, but you still see that you're going to get a mean squared error, which is not going to be impressive here. On the other hand, if I do a decision tree, what you will see then is something like this. So this is a decision tree where I have put the depth of the tree in terms of the variable 2, 5, and 7. So this means that what I'm doing now is if I have a shallow tree, which means max depth equal to 2, I'm actually narrowing this down to very few regions. If I now increase the depth of the tree, I'm opening up for more and more regions, more and more of these rectangular areas. And that means that there will be less observations in each region. Now, what you also see is that with a given depth, what you make now is a prediction. So the prediction which I make for the max depth 2 is going to be the mean value of all the observations which you see here. So that's the prediction in this region. And then you see the prediction in this region, and then you have the prediction here, and the final prediction over here. When you increase the depth of the tree, you see now that you are getting closer to the data points which we want to reproduce. So the data points for the random walker are just given by these black circles. And clearly, when I now make my decision tree deeper and deeper, what I'm doing then is I'm narrowing down the number of observations I have in every small box. So clearly, if I were to rerun this now with a deeper tree, and you can see here the calculations I've made, I'm using the regression decision tree, and I'm setting the max depth to 2, 5, and 7. So if I now were to set this down to, let's say, 11 here, that means I'm going to have less and less observations in one of these small square domains or rectangular domains. And if we try to rerun it, what we are going to see then is something which looks like this. And now you see this is not the max depth equal to 7, but it's actually max depth equal to 11. And suddenly what you see now is that the decision tree is indeed traversing more and more of the data points. And we are going to get a better and better mean squared error with a deeper and deeper tree. The problem, however, which is pretty obvious, and I guess you see that very clearly, is that what you end up with then is a clear example of something which can lead to overfitting, because now we are really trying to traverse every single observation. By that, it means that every prediction we make in these small areas is just the observation itself. There are some very few points where we fail, so we could actually make the tree deeper and deeper. So if we just change this to, let's say now 13 here, and just rerun again. So these algorithms are actually also pretty easy to run. And now you can see that by the eye, it seems now that you're basically traversing almost all the points properly. But that means that if you were to put in a new point in here and have that as a test point, you would fail miserably. So that would be a clear example of overfitting. Now, the algorithms for setting up a decision tree are actually pretty simple. And we are going to look at both these algorithms. And if we want to build a regression tree, normally what we do then is that we keep splitting the areas in smaller and smaller areas. And then we look at the mean values for each area. We calculate the mean squared error for the left and the right areas. And then we try to minimize this function. And then when we've made one split, we continue and perform the next split, and then we can subdivide it more and more and more. But we are going to jump into the classification problem, and then we go back to the regression algorithm for setting it up. So the regression algorithm is a little bit simpler, and we what we are going to do now is to simply to set up the algorithm for the plain classification problem. So let's switch back to the whiteboard here then. So let me just bring the whiteboard back again, and now we're going to develop the classification algorithm for a decision tree. So let's just bring it up and look back at the data which we have. So the classification algorithm, for a tree. So what I said is that we need a way to decide on how we split the tree. So one way to classify a tree is by what is called the information gain, which is normally based on the concept of entropy, which then can be read as the degree of uncertainty or impurity in a given node which we have. You could also read that as a degree of disorder. So the information gain is something which lays the foundation for one of the many algorithms for dealing with this, and it involves the calculation of something which is called the entropy. Now, the entropy contains the degree of impurity and purity of a given node. So if the node is pure, that means that it consists of only one type of observations. If the node is impure, that means it can contain a mix of true and false type of observations. And what we are going to do when we make these trees deeper and deeper is that we are going to purify more and more the different nodes, so that at the end we just have one type of features in one specific final node. That's the kind of ideal which we want to. So if the targets are the outcome of a classification, that's something which can take many types of attributes or features. And what we need to define then is some kind of probabilities in order to calculate the entropy. But there's another quantity which is also widely used in these classification problems, and that's called the Gini factor. Now, the Gini factor is easier to calculate because the entropy involves the calculation of a logarithm. And the calculation of a logarithm is something which normally takes more CPU cycles. So what is common to actually do in many of these calculations is to define something which is called the Gini factor. So what we want to do now, so the overarching idea, is to have nodes which are as pure as possible. So we want them to have nodes with 0 or as less as possible impurity. And I'm going to show this by the example of the final grades in a given course, depending on the number of hours we've studied, or grade trend, and also the number of hours we've been sleeping. So typically we will have many attributes and classes as possible impurity as function of the number of attributes or classes or features as functions of the number of features, and sometimes you will see this also called attributes, properties. I'm just writing etc. here. And this is going to allow us to decide whether a specific node now is composed of only data from one specific class. And the quantities which we normally calculate then, in order to do this, is something which is called the Gini factor, or another quantity which is widely used is normally the entropy. And these are the kind of quantities, the mathematical quantities, which we use to split a tree, to split trees into true and false, and define the different nodes at a given level of the tree, and defines split trees and define nodes. So let's take let's take a look at a very simple case. So if we look at this Gini index, for instance, if we have a Gini index of 0, that means that we have a pure node or pure split, and that contains only one type of attributes or features, and that's going to give a Gini factor of 0. It's also going to give an entropy of 0. So let's suppose we have as a simple example, consider now a case which now has only two classes. So let's take an example. We have two classes with probability. So the first class has a probability which we just call for P. And since the probabilities are discrete and we have two classes, the other one must have probability 1 minus P. So we would have a probability P as one of them, and then we would have probability 1 minus P. So this is a binary system. Now, what we would define then, when we set up the entropy, is something like this. So the entropy is defined as, so this would be S, and this is a sum over the probabilities which we have, or the classes. So this will be go over 1 up to the number of classes. And then we would have the probabilities for each class here. And normally this is done in terms of log 2, but you can also take the normal log actually. So this would be the entropy. And if we look at this specific example which we have, this becomes equal to minus, the first one is just P, and then I have a log 2 of P, and I have minus, and I have 1 minus P multiplied with log 2 of 1 minus P. And we haven't decided what this variable P is going to look like. Now, the Gini factor, and we are coming back to some of these definitions. So the Gini factor is defined as a G equal to 1 minus the sum over the classes which we have, and then multiply with the probability squared. Now, for the specific example which we have here, you can easily see that this sums up to 2 of P or 1 minus P. You can define this in different ways now, but these are the two most common ones. So the whole thing we want now is to find a way to make a split of a given node, and also to use this to define the root node and all the other nodes and how they are going to split. So these are just two possible ways of doing it, but they are some of the simplest possible ways. In order to build up this intuition about the entropy, what you could do now is actually to plot these two quantities. So if I now take the plot of the probability which goes from 0 to 1, so this is a function of the probability, and I take the midpoint which is 0.5, what I would see then with this Gini factor is that this is going to have a behavior like this. So it's going to be 0 at the two endpoints, and you can quickly see that from the expression there. And it's going to have a maximum value at the midpoint. If I take the entropy with respect to the standard log function, that's going to peak at 0.69. If I take the entropy with log 2, that's going to peak at 1. So that's going to have a slightly different behavior. So if we take the log 2, and we're also going to define 0 times log 2 of 0, that's going to be defined to be 0. So in that case, we would get a function which goes like this. And in both cases, what you see now is that when we have probability 1, so that means that if we have the probability equal to 1, that means we are in only one class in this case. If we have a probability p equal to 0, that means that we have the other state. So in here, that means that with p equal to 1, that is a pure state. If I have 0, I have the other pure state. So this would be the other pure state. In the midpoint, however, what I would have is something which represents a mix of the different states. So if we now look at it, so we could now say that 0 here, if we have a 0 Gini factor or 0 entropy, that means that all the data points which we have, all elements in the data, belong to only one of the attributes or classes or features. So that means that all elements belong to only one class, to one specific attribute or class. So these are often used interchangeably as kind of definitions of the different properties we have, attributes, class. If the Gini factor is equal to 1, what that means that all the elements are randomly distributed across various classes. So that means that all elements, all the data points which we're looking at, are randomly distributed across various classes or attributes. And if I have a Gini factor of, a specific case, a Gini factor of 0.5, what that means is that we have a equal distribution of the two classes in our case. So we have opted for a binary problem, and this could be a true-false situation, it could be a yes-no case, or whatever we decide for the binary problem. That means that the nodes equally distributed classes. So we cannot distinguish them. Now, when we are setting up a decision tree, and if we look at this algorithm, which is called the CART algorithm, CART stands for classification and regression tree. The standard method to split a given node into false and true, or whatever we are looking at, is normally done by calculating the Gini factor. The Gini factor does not involve the calculation of the logarithm, which enters the entropy, and that means that the calculations can often be done faster. So what we're going to look at now is actually the CART algorithm, so this classification and regression tree, so CART, with Gini factor. And what we're going to do now is actually to build up a regression tree with a data set which we have made up for these grades and the grade trend and the properties of the number of hours we've slept, the number of hours we've studied, and the final grade for a given course. So we're going to make up a data set with 10 entries. So let's look at that. And then when we have set up the data set, we are then going to calculate the Gini factor, and we're going to figure out how we can set up the root node, how we can set up all the other nodes based on the calculations of the Gini factor. So we are going to look at a binary splitting of each node. But the first node we need to set up is the root node. And that is going to be defined by what the Gini factor is going to give us as the most important feature or class of observations which we have. So the binary splitting is going to be the basic way which we construct a decision tree with. So I see that we are running into break time. After the break, we are going to set up the table with the data points which we are going to use to calculate the Gini factor and set up the calculations which are needed in order to define our decision tree. So let's take a small break and then we meet in. So what we are planning to do now is to demonstrate how you can write your own algorithm for classification and regression for decision tree. And the most common way, which is used in many of the applications, is to calculate something which is called the Gini factor. And the Gini factor is normally used with binary splitting. Now, the example which we're going to look at now, hopefully gives you the kind of insights about how to set up a code yourself. Now, we are going to look at a case which we mentioned before the break, which deals with the grade trend of a given a cohort of students. So let me just take that one away. And we're also going to look at how the number of hours you sleep and how the number of hours you have studied influence the grade of a specific course. So what we're going to say now is that we have a set of features or attributes or classes or properties, whatever you might like to label these. And these are the grade trend from previous classes you've taken, the number of hours you've slept, the number of hours you've studied, and the grade. And what we want to do now by calculating the Gini factor is which one of these classes is going to be the root node, which literally means which of these attributes or classes is the one which is the most important one, which dominates the final grade for this specific course. Is it the number of hours we have studied, or is it the basic grade trend, or is it the number of hours we have slept? Now, what I'm going to do now is just to punch in some values. And for the grade trend, we are going to now look at 10 persons which we have followed. So we are going now to assume that the grade here is above, and then this person has slept less than the number of hours which are normally recommended, something like between 6 to 8 hours. And then we have a high number of hours studied, could be something like more than 10 hours per week, just to give you an example. And then we are going to put the grade above in this case. We have the next person we've been following. So these are just numbers which I made up actually. There is no real data set which I've used actually. So we could now assume that this is somebody who's been able to sleep a little bit better, but studied less, and then got a final result which was below the average grade. And I'm just going to continue to fill in the different results here. So we have a low, and we have a high, and then we have above, and the next one is also an above here. So let me just fill in these entry points. I see I should have made up this table before we actually met. And then we have an above here, and we have below, and below. Now in the code which we have in the Jupyter notebook, we actually read in this data, but I've already converted this data into numbers. And it's pretty common then to just convert above to number 1, below to 0. And you would have 1 here, 1, 0. So when you're running your classification algorithm, you would already have converted these into numbers. Or you can use this encoder functionality, which is included with scikit-learn, where you actually, with these binary classes, you can then convert these into either a binary representation in terms of binary number representation, or you could just convert them into ones and zeros. So you would have 0, 0, 1, and 1. So if you look into the data file which I've made for that specific example in the Jupyter notebook, you would see that the entries are just given by numbers like these. So if we now continue, we would have a high here, So as I said, these are just the data sets which I made up on the fly here. So we would have a high, and then we have a low, and low, and high. And then we continue. So we have a high case. So somebody was able to study a little bit more. We have another high case, and then we have a low one, and then we have a high case, a high one, and a low one, and a high one. And then we have the final grade, which is our output. So we have above, below, and above, and then we have an above here. We have a below, and then another below, and below, below, and yet another below here. This is actually not this course, actually. Everybody does fine here. Actually, project ones have just been a fantastic read. But what you see now, we have 1, 2, 3, and 4 cases where we have above the average grade. And then we have on the grade trend, we have 6 cases which have above grade, the average grade, and 4 below. So what we need to calculate now is the Gini factor of the different classes. And then we simply start by calculating all the attributes classes we have. So we need to calculate the Gini factor for the various classes. So one thing which we see now, if we now look at the trend, we have 10 entries. And if we do the counting here, we see that we have 6 cases which have a grade above and 4 cases which have a grade below. So let's look at the probability for that. So the probabilities now are simply defined by counting the number of cases and divided by the number of total cases. So if we now calculate this P, where we now say grade trend above average, it's easy to see from the table here that this is 6 divided by 10. So I have 6 cases with a grade above average, and I have 4 below. So that means I have P of trend, which is now below the average grade. This is 4 divided by 10. So what I want now is the Gini factor for the trend. So Gini, we just call this grade trend for trend. Gini for trend. So we found the probabilities for above and below for these cases. And now what we are going to match this with is the grade output for this specific course. So what we're going to look at now, if we have now passed trend is above, equal to above, and grade is above, if we now look at our table here, we will see that this probability, so we have 6 cases with the grade, average grade above. And now if we now look at these cases here, we will see that, okay, we have this case above, there's an above grade here. Here we have an above, but that's also above. We have this one, and that matches this one. But then we have this one, which is a below, and we have this one, which is also below. But then we have a final one here, where the final grade is also above. So of the 6 cases where the grade was above, we have only 4 which get a grade above average in this specific course. So that means that the likelihood here is 4 divided by 6. Then, if trend is above and the grade is below, and grade below, then a simple counting tells us that this gives us now a case where we have, if we look at that one, we had 4 above, which lead to a grade above average, but then we have 2 which do not. So this is equal to 2 divided by 6. which is equal to 1/3. Now the Gini index for this specific case, and then we need to weight that one with the probabilities for the different cases. So this Gini index is then 1 minus, so this is 4 divided by 6 to the power of 2 plus 2 divided by 6 to the power of 2, and that's equal to 0.45. But the next thing we need to do now is to look at if the trend is below average, but the grade is above, and grade above. So we remember now that we had 4 cases with a grade below. So if the average grade below, so if we now look at that one, so we have a below here, so there's no above. We have a below here, still below. We have a below here, still below. And we have a below here, which is still below. So in that case, there is 0 probability. So this is simply equal to 0. And then if the trend is now negative or below, and the grade is below, and grade, final grade for the specific course, is below, then this probability is actually 4 divided by 4, which is just 1. So the Gini index for this one is 1 minus, and then I have 0 squared plus 1 squared, which is equal to 0. Then what we need to do is to calculate the weighted sum for this grade trend before this specific course. So the weighted sum then of the probabilities multiplied with the Gini indices, weighted sum for the trend is now given by 6 divided by 10. These are the cases which are positive. That means above 0, above the average. So this is times 45 plus 4 divided by 0, multiplied with 0, and that's going to be equal 0.27. So that is the Gini index for the trend. Now we're going to repeat this exercise, and now we're going to look at hours slept. So Gini for hours slept. And we're going to calculate the same thing again for the hours which we have studied. So what we are doing now is that we are looping over all the attributes, and for each attribute we are now calculating the Gini factor, and the one which is going to have the smallest Gini factor, the one closest to 0, is the one which is the purest one. That means the one which is dominated by one class only. And this is the way we want actually to split our trees. So let's now rerun these calculations, and the recipe is basically the same. So we can now look at the number of hours slept. So the probability for number of hours slept, where you actually got a grade which was above. So now a number of hours slept above the average. So in this case here, if we now go back to the table, we would now see, if we look at the hours slept, we have where we are above the what's expected. So we have 1, 2, 3, and 4 cases, and then we have 6 of the other ones. So the number of hours slept above what is expected is something, gives us now a probability which is equal to 4 divided by 10. And then the probability for the hours slept less is now equal to 6 divided by 10. And now I'm going to repeat this exercise which I had. So if slept is above the average which is expected, and the grade is above, and remember now that we have 4 cases here, then there are only 2 cases where I get a grade which is above. So that's equal to 2 divided by 4, which is a half. And then I have to look at the case if slept above and grade is below. What I have then is a case now where I actually have two grades which are below the average. So in this case, P is also equal to 1/2. And if I now take the and calculate the Gini factor for this specific case, what I'm going to get then is a Gini index for this specific case, which is given by 1 minus, and then I have 1/2 squared plus 1/2 squared, and that's simply equal to 0.5. Then I can repeat the same for hours slept, and the hours slept is below what we would like to have, and whether the grade is above the average or below the average. So I take the next one. So if slept less and grade is above, this has a probability when I just count the number of events I have. This is equal to 2 divided by 6, which is 1/3. And then I have the final case here, if slept less and the grade is below average, then I have a probability P here, which is 4 divided by 6, and that's just 2/3. And that gives me a Gini index for this specific type of event or probabilities, which is given by 0.45. And if I add it up, so the weighted Gini index for sleeping, that is now going to be given by 4 divided by 10. These are the guys who sleep more, multiplied by 0.5, plus 6 divided by 10, multiplied by 0.45, and this is equal to 0.47. So this is, when it comes to the final output, this is a more mixed case. It means that we have a case now where the obtaining a grade below or above the average is more or less a kind of 50-50 case. So that means that we cannot tell exactly whether you slept less or slept more did really influence the grade. So what I'm going to do now, and I leave this as a small exercise to you, that is to simply state the final result. So the weighted Gini for hours studied. In that case, we are going to get a Gini index, which is given by 0.34. So if we now collect everything, we can now set up a feature or attribute of the specific classes which we have and put up the Gini factor. So we have the trend, and that has a Gini factor 0.27. We take the hours we have slept, and that has a Gini factor 0.47. So this is close to 50-50 case. And then we have the hours studied, and that gives us a Gini factor of 0.34. So that means that when we now choose for the root node, we would choose the one which has the smallest Gini factor. That means the one which has the purest kind of features. So the Gini factor, which is smallest, that gives us now a way to define, which is smallest, defines the root node. So let's now start designing the tree here. So what we have is the following. So we have a root node. So this is a root. And this is now defined by the grade trend. So this is the most important feature. And it has a Gini index of 0.27. And it splits in the 10 observations which we made, it splits that into 6 cases which got a grade or a positive result above, and then 4 cases which actually got a grade which is below. So if this is true, which in our case true is above, so we have 6 data points there, and then if it's false, so that means false, which means in our case is below. If we now look at the false case, what we need to look at then is the other 2 attributes, because now we have decided that the grade trend is something which is a dominating node, and now we ask ourselves, what should we look at here? So is it the number of hours slept, or would it be the number of hours we have studied? And we can ask the same question in the false direction. Now, if we look at the false case, if we now write out that in terms of a table here, what we would get then is something like this. So let's take a quick look at this and just write down. So I'm just going to make a more compact table. So T for trend, slept, so that's our sleep for hours of slept, studied, and then the grade. So in this case, what we have are just people which had a grade which was below the average. So I had a B, 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 and B. And then if I look at the sleep here, what I have is high, and then I have low, high, and low. And here I have low, high, high, and high, but the grade here is all below. So when I now look at the grade here, if you look at this column which you have here, so all the grades are below. So that means that what we have in this specific case is a situation where all the grades are the same. And in that case, our tree terminates, because for the people which had a trend, a grade trend which was below average, we end up with 4 situations where all the grades, all the final grades are actually below. If I look at this specific case, if I now take and set up a table with these results, and this is now where I have to calculate the Gini factors again. So if I look at this table and use the same shorthand, T, sleep, studied, and final grade, what I have then is a grade which is above average in all cases. And then I have a sleep which is low, low, and then I have a high, low, low, and high. And then here I have high, high. Actually, this is low, and I have low and high, but the grade is not only above or only below the average. So the grade is still mixed here, because we have 4 people with a grade which is above average, and we have 2 which is below. So we need to actually to purify this box here, and we need to find out whether the number of hours we have slept or the number of hours we have studied is the attribute or class or feature which matters the most for the next splitting of the tree. So in this case, the case to the right here, we have already found an output which is just dominated by one class. So that means that in this specific case, for the false direction, after the root node, we can actually stop with the final leaf, because then if this is false here from the grade trend, if the grade trend is above, we split into a true case with above, and if it's below, the final grade is always below. So that means that this specific case here, that terminates because the output is now pure, whereas in this case, the output is not pure, And now we need to find the Gini index for the number of hours we have slept and the number of hours we have studied. So when we repeat this exercise, we have then to repeat this exercise based on these entries. And obviously, this one is something which we don't calculate because we've already done it. So we need to evaluate the Gini index for sleep and the Gini index for studied. So clearly, if we had more classes here, this would just include more and more classes which we would have to traverse and calculate the Gini factor of. So if I now do the calculations here, what we are going to find is the following. So I'm just going to give you the answers. So if we look at this one, so this is the weighted Gini. For hours studied and hours slept. So if I do the calculations in exactly the same way, and I just leave that as a small exercise to you guys, if I look at that one, we are going to get a Gini factor which is equal to 0 in that case. On the other hand, if I take the weighted, repeat the same exercise, the weighted Gini for hours I have slept, and I'm going to get a Gini factor which is 0.33. So these are the attributes of which I'm calculating the Gini factor of. So with that, we can now set up the final decision tree. So what we have is the following. So we have the root node, and this is defined by the trend, and the trend has a Gini index of 0.27 when we look at all the attributes. So this is the Gini factor which is purest. And here we can then split into those which have a trend which is above. So we have 6 people which have a trend which is above. So this is 6 here. And then we have 4 which have a trend which is below. Now in here, what we have is that the final grade is below. So this is terminates below the average. So this is the final leaf for this specific case. Now, on the other hand, here, what we need to do now is to actually calculate again these quantities, and then we have hours studied, which is the most important feature or most important attribute. And here we have a Gini index of 0. And we split this one into people which studied more. And so this is above or high, as we called it. And then we have 2, so 4, which had a hour study which was higher than an average, and then 2 which were below. And in this specific case, what we end up is final grade below, and then in this case we have a final grade which is above. Now the thing which is nice, as you can see from a decision tree here, is that this is actually something you can bring with you at a party and impress your friends. And it's so simple that you can explain this to everybody. So we see now that the grade trend is the quantity which is the most important one when it comes to the final grade. Then the next quantity, which is the second most important one, is the number of hours we have studied. And the number of hours we have studied leads to a certain number of people which get a final grade above and a final grade below. And we see that in this case, we have more people with a final grade which is above. So this allows us then to actually follow the tree like this and just say that these are the features which matter the most. So if we want to give some advice, we could say, okay, your grade trend is important and also the number of hours you've studied. In a way, we would have expected this. So in a certain sense, this kind of experiment which we did is something which reveals or discloses something which we actually did expect. So you see now the way you would actually build up an algorithm for splitting your tree. You have to traverse all the attributes you have find the one which has the smallest gene index, because that's the one which is purest. If the gene index is equal to 0, that means it's dominated by only one class. And then as you move on, you try to find those features in the next node, which have the smallest gene index. In this case, we actually ended up with our study, which gave a gene index equal to 0. And that's split into two different alternatives, above and below. So when you want to encode this, it's actually pretty straightforward. And the equations you've seen are actually the equations you would have to set up. So you would have to set up, if you look at the calculations we did here, you need to find the probabilities, the total probabilities of hours slept, like here above and below. And then you have the conditional probability that you slept more than average, and you got a grade above average. And similarly, you got a grade below average. And from that, you calculate the two different Gini indices. And then you need to calculate the weighted Gini index. And that gives you the total Gini index for that specific attribute. So this is the basic, one of the basic algorithms for setting up a decision tree. So there's nothing more fancy than this. And decision trees, actually from a mathematical point of view, they are extremely simple and they're very intuitive, and there is not much advanced mathematics. The advanced mathematics comes in setting up the different domains and figure out how we split the tree. So let's go back to the Jupyter notebook and take some look at some of the examples which we have in the Jupyter notebook. So we have let's bring back that one. And please, if there are questions, feel free to ask them. So I just wanted to give you kind of ways by which we set up a classification tree and a regression tree. So we've already discussed these quantities here, like the Gini index and the information entropy. Before we move on, I just wanted to show you how you can visualize the trees. So scikit-learn, together with the package which is called GraphViz, allows you to actually plot the trees, make the trees. And for a specific case, like here we have the breast cancer data. We split into the standard train test, and then we do our fitting. But then you can actually print out the tree, so it produces a so-called dot file. So you would need this dot command installed. And if you do that, you can then produce a tree like the one, so it gives you all the attributes and so on. And this produces a final file. And if we go back to the very first slides which we had up here, you will find something like the tree which you see here. So you can see now that the worst perimeter seems to be the most important feature for this kind of cancer classification problem. And it has a pretty large Gini factor. And it gives you the number of samples, and it splits them into true and false. So true, I think, is a benign tumor, and false is the malignant one. And then it continues like this in setting up the next features and the next features and so on, till you actually end up with a Gini factor which is equal to 0. And that is your terminal point, where you just have one specific class. So using that GraphViz software, you can actually produce these kind of trees. And that's extremely handy when you want to discuss and interpret your model here. So if we go down, let me just go down a little bit here, and then look at the other ways you can visualize your results. So I've plotted another or present another way of doing that. And in this specific case, you can then plot the tree. There's actually a functionality which is called plot tree, which is also pretty useful. And you can see the way it's going to look like. You get the plot of the tree inside your Jupyter notebook. And then clearly, then you have to go back to your data set and look at the specific data set you have and try to analyze that. You can print it out as text. This is another data set which loads the petals of flowers and looks at the petal width. If it's petal width less than a given number, it's class 0. This is your root node. and then it splits into petal width larger than 0.80, and then has another root here, and another root, no, sorry, not another root, but another node, and then the final node here. So this is another way by which you can actually write out the features of a tree. So you have this functionality here, which is called feature names. And then you can display the tree in another way here. So this is just about the width of the petal, whether it's larger or smaller than a specific size which is set up here. So the algorithms for doing this are actually pretty simple. So we have this, one of the most used one is actually called the CART algorithm, which simply stands for classification and regression tree. There's another one which is called the ID-free algorithm, which is based on the information gain, which again uses the entropy. This is also widely used, but the one which is most used is actually this CART algorithm, which we described now using the Gini index. But you can also use the entropy if you want to. But the Gini index is the most used in order to split a tree in two branches. And that's essentially because you don't need to calculate a log of a function. So typically what you would do then is to search for a pair, T case, so this would be the classification case as we have done, and that produces the purest subset using, for example, the Gini factor. And then the cost function, what it tries to do is simply to minimize the ratio between the left and the right, where that measures the impurity of the left-right subset. And this M left / right is a number of instances in the left and right subset. And then you can split it in this training set in two. It splits the subsets using the same logic, and then the subsets of the subsets, and so on and so on. And it normally stops recursing once it reaches the maximum depth, which is normally defined by this parameter we encountered before, which is the max depth. And that becomes a hyperparameter. Or if it cannot, it finds a split that will reduce impurity. A few other hyperparameters which you can look up in the manual for scikit-learn are parameters like the min sample split, the mean samples, minimum samples leave, etc., etc. Now, when it comes to the regression case, here it's actually stated in a simpler way, but let's go back a little bit and look at the regression case, which we have at the beginning of today's Jupyter notebook. So the way it's normally done, so you start by splitting your region into two regions. So this would be two boxes, an R1 and an R2. And then you have a set of observations which now are defined by your observations being less than a value S or larger or equal than a value S. So what you compute then is the expectation, or is actually the mean value or the mean squared error, where you have your output minus the prediction you make in the region R1. So you loop over all the data in R1, and this is the mean value as we discussed. So what you're doing now, so think of you have a data set, a one-dimensional problem like the one we discussed before the break, and you have just split it in two halves. And then you look at the left and the right halves, you calculate the mean value of all the observations in the left half and in the right half, and then you calculate the mean squared error and you try to minimize that one, and you minimize that one by, for instance, adjusting this value S here. So S would normally be just set up as the midpoint between which separates the two domains. So you could define this by randomly assigned numbers or by starting at the midpoint, and then proceed till you have an optimal value for your cost function. And for any J and S, so J is now what defines your region, and S, you define the pair of half planes where this is the mean response. So this is what you actually predict, and this is the mean response for the other one. And then when you find the values of J and S that minimize the above equation, that can be done quite quickly, especially when the number of features is not too large. And then you keep repeating this process, looking for the best predictor and best cut point in order to split the data further so that you can keep minimizing the mean squared error. And The CART algorithm for regression is not so different from the one for classification. So if we look at that one, it now contains, as we described above, it contains now the mean squared error for the left region and the mean squared error for the right region, weighted by the number of observations in the two regions. And then the quantity you want to optimize is actually this mean squared error. And where the prediction you make for each node is the average of all the variables you have in that node. And this is the way you would proceed by making it smaller and smaller. So the binary split, as we discussed, is pretty customary to use. And the reason is that multi-way splits fragment the data too quickly, which often leaves insufficient data at the next level down. And multi-way splits can then be achieved by a series of binary split, and this is normally preferred. So the standard approach then is actually to perform binary splits using, for instance, the Gini factor or the entropy. I think the default value in scikit-learn is actually to use the Gini factor. And when you've done that, you can choose whether you want to do a regression problem or a classification problem. And the standard algorithm is this CART algorithm, classification and regression tree. So the examples which you see here is actually the same example we discussed on the whiteboard, where we look at the grade trend, the hours slept and the hours studied. And then we simply compute the Gini indices, and this is something you will find in these whiteboard notes for today. And then the code which you see an example of here, is a code which actually produces the tree. So it reads in a comma-separated value file. It sets up the training and uses pandas to set up the columns which contains the attributes or the features, and then the target which is given by the grade. So that this is actually the output we want to train against. So in this case, if I have a tree of max depth 2, you can now see that the training is perfect, but actually I'm using all the data, so I've not split into train and test. If I were to make a shallower tree, so you remember now from the graph which we made, the depth of the tree was actually equal to 2. So when we calculated the Gini indices. So if I now do use that one, I should get a worse training, and you see that in this case it's 80%. Now, if you wish to play around a little bit, there is a further example which now has more complicated cases, and this is the reason why I didn't go through that on the whiteboard, because that would take more time. But you could calculate the Gini index for another data set where you now take new features like the weather forecast, which means the outlook, whether it's going to be sunny or rainy or overcast. You look at the temperatures, whether it will be hot, mild, and you see now that these different attributes, they have different sub-attributes as well. So temperature is hot and mild and cool. Outlook is sunny, overcast, or rainy. Humidity is high and normal, so that is only a binary case. And the wind is either weak or strong. And this is whether you would go out for a bike ride or not. So 0 obviously stands you would stay home, and 1 means that you're going out for a ride. And there's a code here which you could play around with and perform the classification of this data set. And again here, what you would see then is if you make a shallow tree, so let's suppose we have a max depth of 2, you would then see that in this case the training just has an accuracy of 73%. If I now decide to make the tree deeper, suppose I have a depth of 7, just a random number I picked here, then we will see that the train accuracy is equal to 100%. Now, down here, you will find a code in case you would like to write your own decision tree. So this is a code which simply implements that the calculation of the Gini factor. And one algorithm which we are not going to spend too much time on, which is actually less used, so this CART algorithm is now the dominant one, is the ID3 algorithm. but we will not spend time on that because the CART algorithm is so simple, and also calculating the Gini index is pretty straightforward. So the codes here may be of interest to take a look at. We are going to pick up the thread here tomorrow before we move on to ensembles. But I wanted to spend some time on the decision trees because the decision tree algorithm enters the setup of a random forest. It enters the setup of a bagged forest, but it enters also these methods, which we will discuss next week in more detail, like boosting methods and extreme gradient boosting and steepest descent boosting and so on, which use a decision tree as a weak learner and then keep improving upon that by having a simple method which is cheap and fast to evaluate. Okay, so this is going to stop today's lecture. Tomorrow we will be back in the lecture hall. So today the lecture hall was occupied by this kind of high school teacher post-education training program. And so tomorrow we meet back in our standard lecture hall. So I'm going to stop the recording now